documentary for sleep. Hello there, and welcome. Tonight I want to take you somewhere special, somewhere beyond the familiar boundaries of our cosmic neighborhood, to a place where mysteries drift through the eternal darkness between stars. As you settle in, perhaps adjusting your pillow just so, letting the weight of the day slowly dissolve into the softness beneath you, I invite you to join me on a journey that begins not with answers, but with questions that have quietly captivated astronomers around the world. You see, something extraordinary happened recently in our solar system, something that challenges our understanding of how isolated we truly are in the vast ocean of space. It's a question that might initially seem far-fetched, perhaps even bordering on the realm of science fiction, but the more we examine the evidence, the more we realize that what we're witnessing might be the beginning of something far more profound than a single cosmic coincidence. What if I told you that we've recently detected an object that traveled here from another star system, a journey that took millions upon millions of years through the cold emptiness of interstellar space? And what if this visitor, this cosmic wanderer we call 3I/ATLAS, wasn't alone, but rather the first detected member of a vast fleet of objects, all making their way through our solar system like ships passing in the cosmic night? Now, before you dismiss this as mere speculation, consider that some of the world's most respected astronomers are quietly discussing this very possibility in their observatories and research centers, poring over data that suggests our solar system might be experiencing something unprecedented in human history. The story begins on a seemingly ordinary night in 2019, when automated telescopes scanning the heavens detected something unusual. At first, it appeared to be just another comet, one of thousands that astronomers track each year as they swing around our sun in their ancient orbits. But as observers continued to monitor this object, designated C 2019 Q4 and later named 2I/Borisov after its discoverer, something didn't quite add up. The trajectory was wrong, impossibly wrong for any object bound to our sun. The speed was too high, the angle too steep, and the path it followed could only mean one thing. This object had come from somewhere else entirely, from the unimaginable distances between stars. By the way, if you're enjoying this cosmic journey tonight, I'd love to know where in the world you're listening from and what time it is there as you drift off to these mysteries. Feel free to like and subscribe if these contemplations of the cosmos help you find that peaceful transition into sleep, and do share in the comments below what draws you to these astronomical wonders. Perhaps you're watching from a city where the light pollution hides most stars, or maybe you're fortunate enough to be somewhere rural where the Milky Way still paints its ancient light across your night sky. There's something beautifully connecting about knowing that others around our planet are contemplating these same cosmic questions as they prepare for sleep. Now, as we return to our mysterious visitor, it's important to understand just how extraordinary this detection truly was. You see, space is incomprehensibly vast, and the distances between stars are so enormous that our minds struggle to grasp them. If you were to shrink our entire solar system down to the size of a dinner plate, the nearest star, Proxima Centauri, would be another dinner plate located about 4 miles away. And between these plates, nothing but emptiness, a void so complete that encountering an object from another star system should be almost impossible. Yet here was 3I/ATLAS, later joined by the confirmation of 2I/Borisov, proving that such encounters not only can happen but do happen. The implications of this discovery ripple outward like waves in a cosmic pond. For all of human history, we've observed comets and asteroids, watching them trace their predictable paths around our sun, bound by gravity's invisible chains to endless loops and ellipses. These objects, we understood, were leftover building blocks from our own solar system's formation, frozen time capsules from 4.6 billion years ago when our sun was young and planets were still coalescing from cosmic dust. But 3I/ATLA and its predecessor Oumuamua, the first confirmed interstellar object detected in 2017, shattered this comfortable understanding. They showed us that our solar system isn't a closed system at all, but rather a small island in a vast ocean, occasionally visited by travellers from unimaginably distant shores. Consider for a moment the journey that 3I/ATLAS must have taken to reach us. This object, perhaps the size of a mountain, has been travelling through interstellar space for millions, possibly billions of years. During its voyage, entire civilizations on Earth rose and fell. The dinosaurs ruled and then vanished. Continents drifted across our planet's surface. Mountains formed and eroded away. And through all of this unimaginable span of time, 3I/ATLAS continued its silent journey through the darkness, moving at speeds that would carry it from Earth to the Moon in just a few hours, yet still taking eons to cross the spaces between stars. The detection of 3I/ATLAS wasn't a matter of luck alone, though certainly fortune played its part. It was also a testament to how far our technology has advanced in recent years. Modern telescopes, equipped with sensitive digital cameras and sophisticated software, scan the skies continuously, comparing images taken minutes apart to detect the slightest movement against the background stars. These electronic eyes never tire, never blink, and they've revolutionized our ability to spot objects that previous generations of astronomers would have missed entirely. So, a very real sense, we're living in the first era of human history when we have the tools to detect these interstellar visitors, which raises a fascinating question. How many such objects passed by unnoticed throughout Earth's history? The mathematics of probability suggests something remarkable. If we've detected 2 or 3 interstellar objects in just a few years of having the capability to spot them, then the actual number passing through our solar system must be enormous. Some calculations suggest that at any given moment there might be thousands of interstellar objects within the orbit of Neptune, drifting through our cosmic neighbourhood like seeds on an invisible wind. Most are too small or too distant for us to detect with current technology, but they're there nonetheless, each one a messenger from another star system, each one carrying information about its place of origin in its composition and structure. What makes 3I/ATLAS particularly intriguing is its behaviour as it approached our sun. Unlike Oumuamua, which remained enigmatically silent and showed unusual acceleration that puzzled scientists, 3I/ATLAS developed a beautiful coma, that fuzzy envelope of gas and dust that gives comets their characteristic appearance. This told us immediately that it contained volatile materials, ices that sublimated as the object warmed in our sun's embrace. Through spectroscopic analysis, astronomers could determine that these ices were remarkably similar to those found in our own solar system's comets, suggesting that the basic chemistry of planetary formation might be universal, or at least common throughout our galaxy. Yet there were differences too, subtle but significant variations that marked 3I/ATLAS as foreign to our solar system. the ratios of certain molecules, the particular mix of ices and dust, all pointed to formation conditions different from those that created our local comets. It was as if 3I/ATLAS carried a chemical passport, stamped with the unique signature of its home star, a star we'll likely never identify among the hundreds of billions that populate our galaxy. This object had witnessed the light of an alien sun, had perhaps passed by planets we'll never see, worlds that might harbour their own mysteries, their own possibilities for life and consciousness. The trajectory of 3I/ATLAS tells its own story. By carefully measuring its position over time and calculating backward, astronomers could determine that it entered our solar system from the direction of the constellation Cassiopeia, though its actual point of origin was likely much more complex than a simple straight line would suggest. Over millions of years, the gravitational influences of countless stars would have altered its path, turning what might have started as a simple ejection from one star system into a complex dance through the galaxy. Each stellar encounter, even distant ones, would have nudged its trajectory slightly, creating a path as intricate as it was long. As 3I/ATLAS swung around our sun, it followed a hyperbolic orbit, a path that would take it back out into interstellar space, never to return. For a brief moment in cosmic time, measured in months from our earthly perspective, this ancient traveller graced our skies, allowing us a glimpse of something from beyond our familiar realm. Astronomers around the world trained their instruments on it, gathering every photon of light, every bit of data they could before it faded back into the darkness. Each observation added another piece to the puzzle, another clue about the nature of these interstellar wanderers. The timing of 3I/ATLAS's discovery, coming so soon after Oumuamua and 2I/Borisov, has led some scientists to wonder if we're witnessing the beginning of something unusual. Perhaps, they speculate, our solar system is entering a region of space more densely populated with interstellar objects. Or perhaps these objects have always been passing through, and we're simply getting better at spotting them. Either possibility is fascinating, but there's a third option that's even more intriguing. What if these objects aren't randomly distributed through space, but instead travel in groups, streams, or even fleets? This isn't as far-fetched as it might initially sound. When a star system forms, not all material ends up incorporated into planets or falling into the central star. Much of it gets ejected into interstellar space through gravitational interactions with forming planets, especially giant planets like Jupiter. If a young star system ejects millions or billions of small objects, and if these ejections happen in waves or clusters, then these objects might travel together through space, maintaining loose associations over cosmic timescales. They wouldn't be travelling in formation like a fleet of ships, but they might follow similar paths, arriving at distant star systems in waves separated by years, decades, or centuries. The physics of such a scenario are complex but not impossible. Objects ejected from the same star system at roughly the same time would have similar velocities and directions, at least initially. Over millions of years, slight differences in their trajectories would cause them to spread out, creating a stream of objects rather than a tight cluster. By the time they reached another star system, like ours, they might arrive spread out over many years, each one appearing to be a solitary traveller when in fact they're all part of the same cosmic diaspora. Consider the implications if this fleet hypothesis is correct. It would mean that 3I/ATLAS is not an isolated visitor, but perhaps a herald of more to come. Over the coming years and decades, we might detect more interstellar objects with similar characteristics, similar trajectories, possibly even similar compositions. Each one would be another piece of evidence supporting the idea that star systems throughout the galaxy are constantly exchanging material, sending fragments of themselves across the vast distances of space, like messages in cosmic bottles. This exchange of material between star systems has profound implications for our understanding of planetary formation, and possibly even the origin of life. If objects like 3I/ATLAS are common, then every star system, including our own, has likely been visited by millions of such objects over its lifetime. Some of these visitors might have impacted planets, delivering water, organic molecules, or other materials from distant stars. In this view, planetary systems aren't isolated islands, but are instead connected by a vast network of travelling objects, each one potentially carrying the seeds of chemistry or even biology from one system to another. The detection of 3I/ATLAS also raises questions about our own solar system's contributions to this interstellar exchange. Just as we receive visitors from other stars, our Sun has undoubtedly sent its own emissaries into the galaxy. Comets and asteroids ejected by Jupiter's gravity, fragments blown off by ancient impacts, all of these are now somewhere out in interstellar space, carrying with them the chemical signature of our solar system. Perhaps, millions of years from now, one of these objects will pass through another star system where intelligent beings will study it with the same wonder. We felt studying 3I/ATLAS. As you lie there tonight, perhaps feeling your breathing slow and deepen as these cosmic contemplations wash over you, consider that above you, beyond the protective blanket of our atmosphere, these interstellar travellers continue their eternal journeys. Right now, at this very moment, there are likely dozens of interstellar objects passing through our solar system, too small or too distant for us to detect. They're witnesses to the galaxy's history, carriers of information about places we'll never visit, participants in a cosmic exchange that's been happening for billions of years and will continue for billions more. The story of 3I/ATLAS is still being written, even as it fades from our telescope's view, heading back into the interstellar darkness. The data it provided continues to be analysed. Scientists are refining their models, adjusting their theories, preparing for the next interstellar visitor, and there will be a next one, of that we can be certain. Whether it arrives next year or next decade, whether it's part of the same hypothetical fleet as 3I/Atlas, or a completely unrelated wanderer, it will add another chapter to this ongoing story of cosmic connection. The possibility that 3I/ATLAS is part of a fleet also changes how we think about searching for these objects. Instead of waiting passively for them to appear in our telescopes, astronomers are now actively looking for patterns, searching for objects with similar orbits or characteristics that might indicate a common origin. New surveys are being planned, more powerful telescopes are being built, and sophisticated software is being developed to sift through the enormous amounts of data these instruments produce. We're entering an era where the detection of interstellar objects might become routine rather than extraordinary. Yet even as these detections become more common, each one remains a source of wonder. Every interstellar object is unique, carrying its own history, its own story of formation and ejection, and cosmic wandering. Some might be ancient, formed in the galaxy's youth when heavy elements were scarce, and star systems looked very different from our own. Others might be relatively young, ejected from star systems that formed around the same time as ours, or even more recently. Each one offers a glimpse into the diversity of planetary systems throughout the galaxy, a small sample of the infinite variety that exists among the stars. The chemical analysis of 3I/ATLAS revealed the presence of cyanogen, a simple molecule made of carbon and nitrogen that's common in our own solar system's comets. This discovery was both familiar and strange, suggesting that some chemical processes are universal, while others might be unique to particular star systems. The presence of familiar molecules in an object from another star suggests that the basic chemistry of the universe is consistent, that the same elements combine in similar ways regardless of where in the galaxy they are. Yet the specific ratios, the particular mix of molecules, these details tell us about the specific conditions under which 3I/ATLAS formed, conditions that were subtly different from those in our own solar system. As we delve deeper into the mystery of 3I/ATLAS and its potential companion objects, we're really exploring fundamental questions about our place in the universe. Are we isolated, separated from other star systems by insurmountable distances? Or are we part of a connected galaxy, linked by streams of travelling objects that carry information, and perhaps even the building blocks of life from star to star? The detection of 3I/ATLAS suggests the latter, painting a picture of a galaxy that's more dynamic, more interconnected than we previously imagined. The technology that allowed us to detect 3I/ATLAS continues to improve at a remarkable pace. Next-generation telescopes, some already under construction, will be able to detect much fainter objects, potentially revealing a population of smaller interstellar visitors that currently escape our notice. These instruments will also be able to study detected objects in greater detail, perhaps even allowing us to determine the specific star system from which they originated. Imagine knowing not just that an object came from another star, but knowing exactly which star, being able to point to a spot in the night sky and say, "That's where this visitor began its journey millions of years ago." The search for patterns among interstellar objects has led to some intriguing preliminary findings. While the sample size is still too small to draw definitive conclusions, some astronomers have noted that the interstellar objects detected so far seem to arrive from certain directions more than others. This could be random chance, a result of our limited observations, or it could hint at streams of objects following similar paths through the galaxy. If the latter is true, it would support the fleet hypothesis, suggesting that we're seeing the first members of groups that might include many more objects. The possibility of fleets of interstellar objects also raises practical considerations for future space exploration. If such fleets exist, they might provide opportunities for close-up study of material from other star systems without the need for interstellar travel. A spacecraft positioned at the right place and time could potentially intercept one of these objects, collecting samples that would tell us about conditions in other star systems. Such a mission would be challenging, requiring precise timing and advanced propulsion technology, but it's not beyond the realm of possibility for future decades. As 3I/ATLAS continues its journey away from our Sun, it carries with it a slight alteration to its trajectory caused by our Sun's gravity. This gravitational deflection is small but measurable, and it means that 3i over ATLAS's path through the galaxy has been forever changed by its encounter with our solar system. In a sense, our sun has left its mark on this interstellar traveller, just as 3i/ATLAS has left its mark on our understanding of the cosmos. This mutual influence, played out countless times across the galaxy, creates a complex web of interactions that connects all star systems in subtle but real ways. In the vast emptiness between stars, where the darkness is so complete that our human minds struggle to comprehend it, objects drift through eternal night on journeys that dwarf any terrestrial conception of distance or time. These cosmic wanderers, these interstellar vagabonds like 3i/ATLAS, exist in a realm so removed from our daily experience that we need to fundamentally shift our perspective to truly appreciate their nature. As you settle deeper into comfort tonight, perhaps pulling your blanket a bit closer, let's explore what these objects really are, where they come from, and what their existence tells us about the hidden dynamics of our galaxy. To understand interstellar wanderers, we must first appreciate the incredible emptiness of interstellar space. If you were to find yourself somehow transported to the void between stars, you would encounter a vacuum more perfect than anything we can create in our most advanced laboratories on Earth. The average density of matter in interstellar space is about 1 atom per cubic centimetre, though in many regions it's even less than that. To put this in perspective, the air you're breathing right now contains about 27 quintillion molecules per cubic centimetre. The contrast is so extreme that calling interstellar space empty almost seems inadequate. It's a void so complete that matter itself becomes exceptional, noteworthy, almost miraculous in its rarity. Yet through this seemingly impossible emptiness, objects like 3i/ATLAS travel for millions upon millions of years. They move through regions where the nearest star might be light years away, where the combined gravitational pull of all the galaxy's stars creates only the gentlest of influences on their trajectories. The temperature in these regions hovers just a few degrees above absolute zero, cold enough that even molecules move sluggishly and chemical reactions essentially cease. In this frozen, timeless realm, our interstellar wanderers drift like seeds on an ocean whose currents are measured not in knots but in kilometres per second, whose shores are star systems separated by distances that light itself takes years to cross. The origin stories of these interstellar objects are as varied as they are fascinating. Most, we believe, were born in the chaotic early days of star system formation, when young stars were still surrounded by vast disks of gas and dust from which planets would eventually coalesce. In these protoplanetary disks, countless small bodies formed through the gradual accumulation of dust grains, growing from microscopic particles to pebbles, from pebbles to boulders, from boulders to planetesimals. But not all of these objects were destined to become parts of planets, or to settle into stable orbits around their parent stars. The process of planetary formation is inherently violent and chaotic, despite the serene appearance of our current solar system. As planets grow, especially giant planets like Jupiter and Saturn, their gravity becomes increasingly disruptive to smaller objects nearby. These gravitational interactions can accelerate small bodies to incredible speeds, flinging them outward with such force that they escape not just the planet's gravity, but the star's gravity as well. It's been calculated that for every planet that forms in a typical star system, millions or even billions of smaller objects are ejected into interstellar space, beginning journeys that will last longer than the current age of the universe. Consider the sheer number of objects this process must produce across the galaxy. Our Milky Way contains an estimated 200 to 400 billion stars, and observations suggest that most of these stars host planetary systems of some kind. If each system ejects millions of objects during its formation, then the galaxy must be filled with trillions upon trillions of these interstellar wanderers, a vast invisible population drifting through the darkness. The space between stars, which seems so empty when we look at it through our telescopes, might actually be populated with a hidden archipelago of frozen worlds, each one too small and dark to see, but collectively representing a significant component of the galaxy's inventory. The composition of these interstellar wanderers tells us stories about their origins and journeys. Objects like 3I/ATLAS, which displayed a bright coma as it approached our Sun, clearly contain volatile ices, substances like water, methane, ammonia, and carbon dioxide that sublimate when heated. These ices formed in the cold outer regions of their original star systems, beyond what astronomers call the frost line, where temperatures were low enough for these substances to condense from gas into solid form. The specific mix of ices, the ratios of different molecules, these details are like fingerprints that can tell us about the conditions in which the object formed. But not all interstellar wanderers are icy comets. Some, perhaps most, are likely to be rocky or metallic, more similar to asteroids than comets. These objects would have formed closer to their parent stars, in regions where the heat prevented ices from condensing. When ejected into interstellar space, these rocky wanderers would carry with them information about the inner regions of their original star systems, regions analogous to where Earth and the other terrestrial planets formed in our own solar system. The diversity of compositions among interstellar objects means that each one potentially offers unique insights into the conditions and processes that shape planetary systems throughout the galaxy. The journey of an interstellar wanderer through the galaxy is a complex dance, influenced by the gravitational fields of billions of stars. While these objects travel in essentially straight lines through the vast emptiness between stars, their paths are subtly curved by the combined gravitational pull of all the galaxy's mass. Over millions of years, these gentle influences accumulate, causing objects to follow elaborate trajectories that wind through the galaxy's spiral arms, rise above and below the galactic plane, and occasionally bring them close enough to a star for us to detect them. The speeds at which these objects travel are remarkable by earthly standards, but quite modest on galactic scales. 3I/ATLAS entered our solar system travelling at about 32 kilometers per second relative to our Sun, fast enough to circle Earth in about 20 minutes, but still taking years to cross from the outer edge of our solar system to its closest approach to the Sun. These velocities are typical for objects moving through our region of the galaxy, reflecting the complex motions of stars as they orbit the galactic centre. Some interstellar wanderers might travel faster, perhaps ejected from their original systems by close encounters with stellar companions or by supernovae, while others might drift more slowly, barely exceeding the escape velocity from their parent stars. The detection of objects like 3I/ATLAS has revolutionized our understanding of how common these interstellar wanderers truly are. Before we actually observed them, theoretical calculations suggested a wide range of possibilities for their abundance. Some models, predicted that interstellar objects should be extremely rare, perhaps one passing through our solar system every million years. Others suggested they might be much more common, with dozens present within Neptune's orbit at any given time. The detection of multiple interstellar objects within just a few years strongly supports the latter scenario, suggesting that our solar system is constantly being visited by these cosmic travelers. This abundance has profound implications for our understanding of planetary system evolution. If interstellar objects are as common as current observations suggest, then every star system in the galaxy has been visited by millions or billions of such objects over its lifetime. Some of these visitors would inevitably collide with planets, delivering material from other star systems. On Earth, such impacts might have contributed to our planet's inventory of water and organic molecules, potentially playing a role in the origin of life. The idea that life's building blocks might have been delivered from another star system transforms these interstellar wanderers from curiosities into potential agents of cosmic chemistry and perhaps even biology. The physical characteristics of interstellar wanderers are shaped by their long journeys through space. Exposed to cosmic rays for millions of years, their surfaces are likely heavily processed, creating a crust of complex organic molecules and altered minerals. This space weathering, as astronomers call it, means that the surface of an object like 3I/ATLAS might be very different from its interior, with the outer layers recording the history of its interstellar journey, while the interior preserves information about its original formation. Understanding these objects fully requires looking beyond their surfaces to the pristine material within. The rotation of interstellar objects provides another window into their histories. Objects ejected from star systems often carry with them angular momentum from their last gravitational encounters, causing them to tumble through space in complex patterns. The unusual rotation of Oumuamua, the first detected interstellar object, suggested it might have been shaped by collisions or tidal forces during its ejection. 3I/ATLAS, being an active comet, was harder to study in this regard, as the jets of gas from its surface could alter its rotation. These rotational characteristics are like forensic evidence, offering clues about the violence of their ejection and any subsequent encounters they might have had during their journeys. Temperature is another fascinating aspect of these cosmic wanderers. In the deep cold of interstellar space, these objects cool to just a few degrees above absolute zero, colder than anything naturally occurring in our solar system. At these temperatures, even substances we think of as gases on Earth become solid, and chemical reactions essentially stop. The objects become time capsules, preserving their composition unchanged for millions of years. Only when they approach a star like our Sun do they warm up, awakening from their cosmic slumber and potentially releasing gases that have been frozen for eons. The size distribution of interstellar wanderers is still largely unknown, but it's likely to follow patterns similar to objects in our own solar system. For every large object like 3I/ATLAS, there are probably thousands of smaller ones, ranging down to tiny grains of dust. The smallest interstellar particles, microscopic grains of dust, are actually easier to detect in some ways than larger objects. These grains reveal themselves through their effects on starlight, creating subtle patterns of extinction and reddening that astronomers can measure. Studies suggest that a significant fraction of the dust in our solar system might actually be interstellar in origin, tiny visitors that arrived long ago and became incorporated into our local environment. The gravitational focusing effect of our Sun plays a crucial role in determining which interstellar objects we can detect. As these objects approach our solar system, the Sun's gravity bends their trajectories, focusing objects from a large volume of space into paths that bring them closer to the Sun. This gravitational lensing effect means that our solar system acts like a cosmic funnel, temporarily concentrating interstellar objects and making them easier to detect. The effect is strongest for slower moving objects, which spend more time under the Sun's gravitational influence and thus experience greater deflection. Seasonal variations in our ability to detect interstellar objects add another layer of complexity to understanding their true abundance. Earth-based telescopes can only observe certain parts of the sky at certain times of year, and the Sun's glare blocks out large regions where interstellar objects might be approaching. Space-based telescopes avoid some of these limitations, but have their own constraints in terms of field of view and sensitivity. The objects we've detected so far might represent only a small fraction of those actually passing through our solar system, visible to us only because they happen to approach from directions we were watching at times when we could see them. The chemical diversity among interstellar wanderers offers a unique opportunity to study the variety of planetary formation environments throughout the galaxy. Each object carries the chemical signature of its birthplace, preserved in the ratios of different isotopes, the presence or absence of certain molecules, and the overall elemental composition. By studying many such objects, we can begin to build a picture of how planetary formation varies with stellar mass, age, metallicity, and environment. It's like conducting a galaxy-wide survey of planetary systems, but instead of travelling to distant stars, we wait for pieces of those systems to come to us. The possibility that some interstellar wanderers might be artificial in origin has been seriously discussed in scientific circles, particularly after the unusual characteristics observed in Oumuamua. While the vast majority of scientists believe all detected interstellar objects are natural, the possibility of artificial objects cannot be entirely ruled out. If technological civilizations exist elsewhere in the galaxy, and if they engage in large-scale space activities, some of their artifacts might eventually escape into interstellar space, becoming technological wanderers among the natural population. The search for signs of artificiality in interstellar objects has become a small but legitimate part of SETI, the search for extraterrestrial intelligence. The dynamics of how interstellar wanderers interact with our solar system's existing population of comets and asteroids is complex and fascinating. When an interstellar object passes through, its gravity, however weak, slightly perturbs the orbits of nearby objects. Over cosmic time scales, many such passages could significantly alter the orbital distribution of our solar system's small bodies. Conversely, encounters with our solar system's objects could occasionally capture an interstellar wanderer, transforming it from a cosmic nomad into a permanent resident. Some astronomers have suggested that a small percentage of the comets and asteroids we see today might actually be captured interstellar objects, naturalized citizens of our solar system. The study of interstellar wanderers has implications for understanding the future of our own solar system. Billions of years from now, as our sun evolves into a red giant and then a white dwarf, the orbits of planets and small bodies will be dramatically altered. Many objects currently in stable orbits will be ejected into interstellar space, beginning their own journeys as cosmic wanderers. Our solar system will contribute its own fleet to the galaxy's population of interstellar objects, sending pieces of our cosmic neighborhood to visit distant stars long after Earth itself has ceased to exist. As we contemplate these interstellar wanderers tonight, drifting through space on journeys almost beyond imagination, we're really contemplating the deep connections that exist throughout our galaxy. These objects are messengers, carriers of information across distances no spacecraft will traverse for centuries or millennia to come. They remind us that our solar system is not an island, but part of a vast archipelago of star systems, all exchanging material in a slow, cosmic circulation that has been ongoing for billions of years and will continue for billions more. Scientists have begun to notice curious patterns in these interstellar visits, patterns that emerge slowly from the data like constellations becoming visible as your eyes adjust to darkness. As you continue to relax tonight, perhaps feeling the gentle weight of drowsiness beginning to settle over you like a comfortable blanket, let's explore these intriguing patterns that suggest something far more organized than random chance might be at work in the cosmos above us. The trajectories, the timing, the characteristics of these interstellar visitors all hint at underlying structures and processes that we're only beginning to understand. Patterns that might reveal fundamental truths about how our galaxy organizes and reorganizes itself over cosmic time. When astronomers first detected Oumuamua in 2017, it seemed like a singular event, a cosmic coincidence that we were fortunate enough to witness. The calculation suggested we might wait decades or even centuries before seeing another interstellar visitor. Yet just 2 years later, 2I/Borisov appeared, followed by strong candidates like 3I/Atlas, and suddenly what seemed exceptional began to look more like a pattern. This clustering of detections could be explained by improvements in our detection capabilities, but some astronomers wonder if there's more to it, if perhaps we're witnessing the leading edge of a wave of interstellar objects passing through our region of the galaxy. The concept of patterns in the distribution of interstellar objects isn't merely speculative, it's grounded in solid astrophysical reasoning. When stars form in stellar nurseries, they don't form in isolation, but in groups and clusters, sometimes hundreds or thousands of stars emerging from the same vast cloud of gas and dust. These stellar siblings initially move together through space, and even after the cluster disperses, the stars maintain similar velocities and directions for millions of years. If each of these stars ejects objects during planetary formation, those objects would also share similar trajectories, creating streams or rivers of interstellar wanderers flowing through the galaxy. Consider the mathematics of such streams. If a stellar cluster containing 1,000 stars formed 100 million years ago, and each star ejected 1 million small bodies during planetary formation, that's 1 billion objects all travelling in roughly the same direction at roughly the same speed. Over time, small differences in velocity would cause the stream to spread out, becoming more diffuse, but the objects would still maintain a statistical association. When such a stream encounters our solar system, we wouldn't see all billion objects at once, but rather a gradual increase in the rate of interstellar visitors, perhaps lasting centuries or millennia as the densest part of the stream passes through. The search for these patterns requires sophisticated statistical analysis of the limited data we have. Astronomers look not just at the trajectories of individual objects, but at the distribution of their radiance, the points in the sky from which they appear to originate. If interstellar objects were truly random, these radiants should be evenly distributed across the sky. but preliminary analyses suggest there might be preferred directions, regions of the sky from which interstellar objects are more likely to arrive. These preferred directions could indicate streams of objects, or they could reflect the motion of our solar system through regions of varying object density. The velocity distribution of interstellar objects provides another clue to underlying patterns. Objects ejected from star systems should have a range of velocities, depending on the details of their ejection, but this range isn't unlimited. There's a minimum velocity needed to escape a star's gravity, and a maximum velocity that gravitational interactions can reasonably impart. The velocities of the interstellar objects detected so far fall within the expected range. But as we detect more objects, patterns in this velocity distribution might emerge. For instance, if we find a cluster of objects all travelling at very similar speeds, it would strongly suggest they share a common origin. Temporal patterns in the arrival of interstellar objects are particularly intriguing. If these objects travel in streams or fleets, we might expect to see variations in the detection rate over time, periods when interstellar objects are more common, alternating with periods when they're rare. The timescales involved could range from years to centuries, making it difficult to identify such patterns with only a few years of observations. However, as our detection capabilities improve and our observation period lengthens, these temporal patterns should become clearer. The chemical composition of interstellar objects might also show patterns related to their origins. Stars of different masses and ages produce different mixtures of elements through nuclear fusion, and these differences are reflected in the compositions of planets and small bodies that form around them. If a stream of interstellar objects all came from the same stellar nursery, they might share similar compositional signatures, distinct from objects originating elsewhere. The detection of multiple objects with similar unusual compositions would be strong evidence for a common origin. One of the most fascinating patterns astronomers are searching for involves correlations between different characteristics of interstellar objects. For example, is there a relationship between an object's velocity and its composition? Do objects arriving from certain directions tend to be more icy or more rocky? These correlations, if they exist, would provide valuable insights into the processes that eject objects from star systems and the environments in which different types of objects form. The role of galactic structure in creating patterns of interstellar objects is an area of active research. Our galaxy's spiral arms, regions of higher star density where star formation is particularly active, might produce more interstellar objects than the spaces between arms. As our solar system orbits the galactic center, it periodically passes through these spiral arms, potentially encountering higher densities of interstellar objects. The period of this passage, roughly every 100 million years, might create long-term variations in the rate at which interstellar objects visit our solar system. Gravitational perturbations from giant molecular clouds, massive aggregations of gas and dust that populate our galaxy, could also create patterns in the distribution of interstellar objects. When a stream of objects passes near such a cloud, the cloud's gravity can focus or disperse the stream, creating regions of higher and lower object density. Our solar system's passage through these perturbed regions would result in variations in the detection rate of interstellar objects, another pattern hidden in the cosmic dark. The influence of stellar encounters on patterns of interstellar objects adds another layer of complexity. Stars don't maintain fixed positions in the galaxy, but move in complex orbits, occasionally passing close to one another. When our Sun has a close encounter with another star, which happens roughly every 100,000 years, it can gravitationally perturb the Oort cloud, the vast sphere of icy bodies that surrounds our solar system. These perturbations can send comets into the inner solar system, but they can also affect the trajectories of passing interstellar objects, potentially focusing them toward or away from the regions where we can detect them. Patterns might also exist in the physical characteristics of interstellar objects, such as their sizes, shapes, and rotational properties. If objects are preferentially ejected from star systems under certain conditions, those conditions might favor particular sizes or shapes. For instance, tidal disruption during ejection might tend to produce elongated objects, or collisional grinding might favor certain size distributions. As we detect more interstellar objects and characterize their physical properties, these patterns should become apparent. The seasonal visibility of interstellar objects from Earth creates its own patterns that must be carefully separated from intrinsic patterns in the object distribution. Objects approaching from certain directions are easier to detect at certain times of year, and this observational bias could create apparent patterns that don't reflect the true distribution. Sophisticated statistical techniques are required to account for these biases and reveal the underlying patterns in the data. The possibility of multiple populations of interstellar objects, each with its own patterns and characteristics, is another intriguing avenue of investigation. Just as our solar system contains distinct populations of comets and asteroids, with different origins and histories, the galaxy's population of interstellar objects might consist of multiple components. Young objects recently ejected from star systems might have different characteristics from ancient objects that have been wandering for billions of years. Objects ejected by supernovae might have different velocities and compositions from those ejected by planetary migration. Patterns in the detection of interstellar objects might also reveal information about the galaxy's history. Major events like the formation of spiral arms, the merger of satellite galaxies, or waves of star formation triggered by supernovae could all leave their signatures in the distribution of interstellar objects. By studying these patterns, we might be able to reconstruct aspects of our galaxy's past that are otherwise difficult to observe. The search for patterns extends to the question of whether some interstellar objects might be gravitationally bound to our galaxy, or even to local groups of stars. While most interstellar objects have velocities that will eventually carry them out of the galaxy entirely, some might be travelling slowly enough to remain bound, orbiting the galactic centre on vast, complex trajectories. These bound objects would have different patterns of motion from unbound objects, potentially creating distinct populations with different detection probabilities. As our ability to detect and track interstellar objects improves, we're developing new techniques for pattern recognition. Machine learning algorithms trained on simulations of interstellar object populations can identify subtle patterns that might escape human notice. These artificial intelligence systems can process vast amounts of data, looking for correlations and structures across multiple dimensions of parameter space. The patterns they reveal might challenge our current understanding of how interstellar objects are produced and distributed. The connection between patterns in interstellar objects and patterns in other astronomical phenomena is an area of growing interest. For instance, are there correlations between the rate of interstellar object detection and solar activity? Does the solar wind, which varies with the 11-year solar cycle, affect our ability to detect certain types of objects. These connections, if they exist, would add another layer of complexity to the patterns we observe. Looking deeper into the nature of these patterns, we must consider the role of chaos in shaping the distribution of interstellar objects. The three-body problem, a famous challenge in celestial mechanics, tells us that the gravitational interaction of three or more bodies can produce chaotic, unpredictable behavior. In the context of planetary formation and object ejection, this chaos might create complex patterns that appear random on small scales but show structure on larger scales. Understanding these chaotic patterns requires sophisticated mathematical tools and extensive computer simulations. The preservation of patterns over cosmic timescales is remarkable when you consider the many processes that could disrupt them. Gravitational interactions with stars and molecular clouds, collisions between objects, and the gradual evolution of orbits due to subtle effects like gravitational radiation all work to erase patterns and randomize distributions. The fact that we might still be able to detect patterns in the distribution of interstellar objects tells us something profound about the robustness of these structures and the processes that create them. As we explore these patterns tonight, we're really exploring the hidden architecture of our galaxy, the invisible structures that organize the movement of matter on scales vast beyond imagination. These patterns connect us to distant stars and ancient events, creating a web of relationships that spans both space and time. The detection of each new interstellar object adds another data point, another piece of the puzzle, gradually revealing the grand design that underlies what might at first appear to be cosmic randomness. What if 3I/ATLAS wasn't a solitary traveller, but a scout for something larger, a member of a vast fleet of objects making their way through our solar system, like ships passing in the cosmic night? This question, which might sound like science fiction, is actually being seriously considered by astronomers around the world, and as you drift deeper into relaxation tonight, let's explore this fascinating possibility that could fundamentally change how we understand our place in the galaxy. The mathematics of orbital mechanics, combined with our growing understanding of how planetary systems form and evolve, suggest scenarios where groups of objects could travel together through interstellar space, maintaining loose associations over millions or even billions of years. The fleet hypothesis begins with understanding how objects are ejected from star systems in the first place. When a planetary system forms, it doesn't happen smoothly or peacefully. Instead, it's a chaotic process involving countless collisions, near misses, and gravitational interactions that can send objects flying in all directions. Imagine, if you will, a cosmic game of billiards played out over millions of years, where the balls are planetesimals and the cue stick is the gravity of forming planets. In this game, many balls end up in the pockets, becoming parts of planets or moons, but many others are knocked clear off the table entirely, beginning journeys into interstellar space. The key insight that leads to the fleet hypothesis is that these ejections don't happen randomly over time but tend to occur in waves or episodes. During certain periods of a star system's evolution, the ejection rate can increase dramatically. For instance, when a giant planet like Jupiter migrates inward or outward through the disk of planetesimals, it can trigger a cascade of ejections, sending millions of objects into interstellar space within a relatively short period, perhaps just a few million years. These objects, ejected during the same episode, would have similar velocities and directions, at least initially. Consider what happens to such a group of objects after ejection. They don't stay together in a tight formation. That would be impossible given the slight differences in their velocities and the perturbations they experience. Instead, they spread out along their direction of travel, forming what astronomers call a stream or flux tube. The fastest objects race ahead while the slowest ones lag behind, and objects with slightly different lateral velocities spread out perpendicular to the main direction of travel. Over millions of years, what started as a relatively compact group of objects becomes a vast diffuse stream, perhaps light years long and wide. Now imagine this stream of objects, this fleet if you will, encountering our solar system. We wouldn't see them all arrive at once like an invasion fleet from a science fiction movie. Instead, the encounter would play out over years, decades, or even centuries. The first objects to arrive would be the fastest ones, or those whose trajectories happen to bring them closest to our detection capabilities. These would be followed by the main body of the stream, where the object density is highest, and finally by the stragglers at the tail end. From our perspective on Earth, it would appear as a gradual increase in the rate of interstellar object detection, followed by a peak and then a gradual decline. The mathematical modelling of these fleets is complex but revealing. Using sophisticated computer simulations, astronomers can track the evolution of groups of ejected objects over billions of years, accounting for the gravitational influences of stars they pass near, the overall gravitational field of the galaxy, and even the subtle effects of gravitational radiation. These simulations show that while streams of objects do disperse over time, they can maintain coherent structures for remarkably long periods, especially if the objects are moving at similar velocities relative to the local stellar population. The detection of 3I/ATLS and other recent interstellar objects has provided data that can be tested against these fleet models. While the sample size is still small, some intriguing hints have emerged. The velocities of the detected objects, their approach directions, and even some aspects of their compositions show similarities that, while not conclusive, are consistent with the possibility that they might be related. It's as if we're seeing the first few raindrops of an approaching storm, not yet enough to be certain a storm is coming, but enough to make us look more carefully at the clouds on the horizon. The implications of the fleet hypothesis extend far beyond simple curiosity about patterns in astronomical data. If interstellar objects do travel in fleets, it would mean that encounters between star systems and groups of foreign objects are more common and more significant than previously thought. These encounters could have played important roles in the evolution of planetary systems, including our own. Impacts from fleet objects could have delivered water and organic molecules to young planets, potentially influencing the development of life. They could also have caused extinctions or climate changes, acting as agents of both creation and destruction. The formation mechanisms for these fleets are diverse and fascinating. One scenario involves the disruption of a star system by a close stellar encounter. When two stars pass close to each other, their gravitational interaction can completely destabilize any planetary systems they might have, ejecting planets and smaller objects in all directions. But because the ejection is triggered by a single event, many of the ejected objects would have similar velocities and directions, forming a fleet. Such stellar encounters are rare but not impossible, occurring perhaps once every few 100 million years for a typical star. Another mechanism involves the death throes of a star system. When a star evolves into a red giant and eventually a white dwarf, the changing gravitational field can destabilize the orbits of planets and small bodies. Objects that were in stable orbits for billions of years suddenly find themselves on escape trajectories. Again, because the destabilization happens over a relatively short period, the ejected objects would form a stream or fleet. Given that billions of stars in our galaxy have already gone through this evolution, the cumulative effect could be enormous numbers of objects travelling in age fleets through interstellar space. Binary star systems, which make up a significant fraction of all star systems, provide yet another mechanism for fleet formation. The complex gravitational dynamics of binary systems can create regions of instability where objects cannot maintain stable orbits. Over time, these regions can accumulate objects that are then ejected in groups when the binary orbit evolves or when the system encounters a third star. The fleets produced by binary systems might have distinctive characteristics, such as higher velocities or more diverse compositions that could help identify them. The concept of resonant ejection adds another layer of sophistication to the fleet hypothesis. In a forming planetary system, gravitational resonances, special orbital configurations where planets exert regular, repeated forces on each other, can create zones where small bodies are systematically ejected. These resonances can act like cosmic pumps, steadily ejecting objects in preferred directions with preferred velocities. The result would be not a single fleet, but a series of fleets, launched at regular intervals like trains leaving a station. The preservation of fleet structure over cosmic timescales depends on several factors. The velocity dispersion of the objects, essentially how different their speeds are, determines how quickly the fleet spreads out. The local stellar density affects how often the fleet encounters stars whose gravity might disrupt it, and the overall gravitational field of the galaxy slowly shapes the fleet's trajectory, potentially focusing or dispersing it. Understanding these factors requires sophisticated modelling that pushes the limits of our computational capabilities. Observational strategies for detecting fleets are being developed and refined. Instead of waiting passively for interstellar objects to appear, astronomers are beginning to search actively for patterns that might indicate an approaching or passing fleet. This involves looking for subtle correlations in the orbits of detected objects, searching for objects with similar compositions or physical characteristics, and monitoring specific regions of the sky where fleet members might be more likely to appear. It's like trying to spot a school of fish in the ocean by looking for patterns in the occasional fish that breaks the surface. The technological requirements for definitively confirming or refuting the fleet hypothesis are substantial but achievable. We need more sensitive telescopes to detect smaller and fainter interstellar objects, increasing our sample size. We need better spectroscopic capabilities to determine the compositions of these objects in detail, looking for chemical signatures that might indicate common origins, and we need longer observation baselines to track how the detection rate changes over time, potentially revealing the passage of fleets. The fleet hypothesis also raises intriguing possibilities for future space missions. If we could predict when and where fleet members might pass close to Earth, we could potentially send spacecraft to intercept them, collecting samples that would tell us about their origins and histories. Imagine being able to study material from dozens of different objects, all from the same original star system, providing a comprehensive picture of how that system formed and evolved. It would be like conducting archaeology on a cosmic scale, piecing together the history of a distant star system from the fragments it sent our way. The connection between the fleet hypothesis and the search for extraterrestrial life adds another dimension of interest. If fleets of objects can carry material between star systems, they might also carry microorganisms or the chemical precursors to life. A fleet originating from a star system where life had evolved could potentially seed multiple other systems with biological material. This mechanism, called lithopanspermia, has been proposed before for individual objects, but fleets would make it much more efficient and likely. The passage of a fleet through our solar system billions of years ago might have played a role in the origin of life on Earth. Statistical analysis of the limited data we have provides tentative support for the fleet hypothesis. The rate at which we've detected interstellar objects is higher than many pre-detection models predicted, suggesting either that our models were wrong or that we're in a period of enhanced activity. The latter possibility is consistent with the passage of a fleet. Additionally, some astronomers have noted that the orbital characteristics of the detected objects show less diversity than would be expected from a truly random sample, though the small sample size makes this observation preliminary at best. The cultural and philosophical implications of the fleet hypothesis are profound. If confirmed, it would mean that our solar system is not as isolated as we thought, that we're regularly visited by armadas of objects from distant stars. It would transform our understanding of our cosmic neighborhood from a collection of isolated islands to a dynamic, interconnected network where material and perhaps information flows between star systems. This vision of a connected galaxy, where star systems communicate through fleets of wandering objects, is both humbling and inspiring. The fleet hypothesis also has implications for understanding the future of our own solar system. If other star systems produce fleets of ejected objects, then our solar system must have done the same during its formation. Somewhere out in the galaxy, there might be fleets of objects that originated here, carrying information about our solar system's early history to distant stars. And billions of years from now, as our sun evolves and dies, it will launch new fleets into the galaxy, ensuring that some trace of our solar system survives even after Earth itself is gone. As we consider the fleet hypothesis tonight, we're really contemplating the possibility that the universe is far more organized and interconnected than it appears. What seems like random encounters between our solar system and interstellar objects might actually be structured events, the result of processes that play out over millions of years and light-years of space. The detection of 3I/ATLAS might not be an isolated event, but part of a pattern that we're only beginning to perceive, like seeing the first few notes of a cosmic symphony that has been playing since the galaxy was young. Each interstellar visitor carries within it the chemical fingerprints of its home, messages written in molecules and isotopes that tell stories of distant suns we see as mere points of light in our night sky. As you continue your journey towards sleep tonight, perhaps feeling your thoughts becoming softer and more fluid like clouds drifting across a moonlit sky, let's explore how these cosmic messengers bear news from stars we'll never visit, carrying information across the vast darkness that separates the islands of light in our galaxy. Through careful observation and analysis, scientists can read these chemical stories, decoding messages that were written millions or billions of years ago in the fires of alien suns and the cold depths of foreign planetary systems. The concept of chemical messages from other stars begins with understanding that every star is unique in its composition, like a fingerprint or a signature. when the universe was young, shortly after the Big Bang, it contained only the simplest elements: hydrogen, helium, and tiny traces of lithium. All the heavier elements, what astronomers call metals, though they include elements like carbon, oxygen, and silicon that chemists wouldn't consider metallic, were forged later in the nuclear furnaces of stars. Each generation of stars creates heavier elements through fusion, and when these stars die, they scatter these elements into space where they become incorporated into new stars and planets. This process of element creation and dispersal means that stars of different ages have different compositions. The oldest stars, formed when the universe was young, contain very few heavy elements. Younger stars, formed from gas enriched by previous generations of stellar evolution, contain more. Even stars of the same age can have different compositions depending on their local environment, the particular mix of gas and dust from which they formed. These differences, though sometimes subtle, create unique chemical signatures that are preserved in the planets and smaller bodies that form around each star. When an object like 3I/ATLAS forms in the cold outer regions of a planetary system, it incorporates the chemical signature of its parent star. The specific ratios of different elements, the particular isotopes present, the trace elements that might be abundant in one system and rare in another, all of these details are frozen into the object's composition. Even after millions of years of travelling through interstellar space, exposed to cosmic rays and the slow processes of space weathering, the bulk composition remains unchanged, a permanent record of the object's origin. The tools astronomers use to read these chemical messages are remarkably sophisticated. Spectroscopy, the analysis of light broken down into its component wavelengths, allows us to identify specific molecules and atoms in distant objects. When sunlight reflects off an interstellar visitor, or when the object emits its own light through fluorescence or thermal radiation, each molecule and atom adds its unique signature to the spectrum. It's like each chemical species is singing its own note, and by analysing the full spectrum we can identify all the voices in the cosmic choir. For 3I/ATLAS specifically, spectroscopic observations revealed the presence of diatomic carbon, cyanogen, and other molecules common in comets from our own solar system. But the relative abundances were different, the ratios not quite matching what we see in local comets. These differences are subtle but significant, like hearing a familiar song played in a different key. They tell us that while the basic chemistry of planetary formation might be universal, the specific conditions under which 3I/ATLAS formed were different from those in our solar system. Isotope ratios provide particularly valuable information about an object's origin. Isotopes are versions of the same element with different numbers of neutrons, and their ratios can vary depending on the conditions under which they formed. For instance, the ratio of deuterium to hydrogen, or the ratios of different oxygen isotopes, can tell us about the temperature and radiation environment where the object formed. These ratios are like timestamps and location stamps, recording when and where in its parent system the object came together. The presence or absence of certain molecules can also tell us about the stellar environment from which an interstellar visitor originated. Stars of different types emit different spectra of ultraviolet radiation, and this radiation can create or destroy molecules in the surrounding planetary disk. A planetary system around a hot blue star would have different chemistry from one around a cool red star. The molecular inventory of an interstellar object thus tells us something about the type of star it came from, even if we can never identify the specific star. Organic molecules, those containing carbon, are of particular interest when found in interstellar visitors. These molecules are the building blocks of life as we know it, and their presence in objects from other star systems tells us about the potential for life throughout the galaxy. Complex organic molecules have been detected in interstellar space and in meteorites, but finding them in confirmed interstellar objects would be even more significant. It would show that the chemistry that leads to life might be common throughout the galaxy, occurring in many different stellar environments. The distribution of volatile and refractory materials in interstellar objects provides information about the temperature structure of their parent systems. Volatile materials, those that evaporate easily like water and carbon dioxide, can only condense into solid form beyond what astronomers call the snow line, far from the parent star. Refractory materials, those that remain solid even at high temperatures, can form closer to the star. The mix of these materials in an interstellar object tells us where in its parent system it formed, providing a map of that system's architecture. Interestingly, the chemical messages carried by interstellar objects aren't just about their parent systems. They also tell us about the interstellar medium through which they've travelled. As these objects journey through space, they are exposed to cosmic rays, high-energy particles that can alter their surface chemistry. They might also collect interstellar dust grains, adding a veneer of material from the space between stars. Reading the full chemical message requires distinguishing between the original composition and these later additions, like separating the original text of an ancient manuscript from later annotations. The possibility that interstellar objects might carry prebiotic molecules or even microorganisms adds another layer to their role as messengers. While the harsh conditions of interstellar space make it unlikely that active life could survive such journeys, dormant microorganisms or the complex molecules that could seed life might be preserved in the protected interiors of these objects. If life is common in the galaxy, interstellar objects could be vectors for its spread, carrying biological messages along with chemical ones. The chemical diversity among interstellar objects, even in the small sample we've detected so far, suggests that planetary systems throughout the galaxy exhibit a wide range of compositions. This diversity is actually encouraging for the search for life, as it suggests that nature has performed many experiments in planetary chemistry. Some of these experiments might have produced conditions even more favourable for life than those in our own solar system. Each interstellar visitor gives us a glimpse of one of these experiments, a sample from nature's vast laboratory. Advanced spectroscopic techniques currently being developed will allow us to read these chemical messages in much greater detail. Next-generation telescopes will be able to detect fainter spectral lines, identifying trace molecules that current instruments miss. Laboratory experiments that recreate the conditions of interstellar space help us understand how the chemical signatures we observe relate to the original composition and subsequent processing. It's like developing better tools for translating an ancient language, allowing us to extract more meaning from the messages these objects carry. The temporal aspect of these chemical messages is particularly fascinating. An interstellar object that formed 5 billion years ago carries information about the galaxy as it was then, when different stars shone and the overall chemical composition of the galaxy was different. Objects of different ages arriving at our solar system provide snapshots of the galaxy's chemical evolution, like core samples that geologists use to study Earth's history. By analysing many such objects, we could potentially reconstruct how the galaxy's chemistry has changed over cosmic time. The role of supernovae in creating chemical diversity among interstellar objects adds another dimension to these messages. When a massive star explodes as a supernova, it creates and disperses heavy elements in a sudden, violent event. Planetary systems forming near recent supernovae would be enriched in these elements, while those forming in quieter regions would have different compositions. Interstellar objects thus carry information not just about their parent stars, but about the broader stellar environment in which those stars formed. The possibility of using chemical messages to identify the specific parent stars of interstellar objects is tantalizing but challenging. While we can determine general characteristics like age and metallicity, pinpointing the exact star requires much more precise measurements and a comprehensive database of stellar compositions. Future missions might achieve this level of precision, allowing us to point to a specific star in the night sky and say, "That's where this visitor began its journey." It would be like solving a cosmic mystery, tracing a message back to its sender across the vast expanses of space and time. The preservation of chemical messages over the enormous timescale of interstellar travel is remarkable. These objects experience temperatures just a few degrees above absolute zero, conditions where chemical reactions essentially stop. They're exposed to cosmic rays that can alter surface chemistry, but generally don't penetrate deep into the object. They might experience occasional heating from passing close to stars, but these events are rare. The result is that the chemical messages remain largely intact, like letters sealed in bottles that have drifted across a cosmic ocean. The chemical messages from interstellar objects also inform our understanding of our own solar system's history. By comparing the compositions of interstellar visitors with our local comets and asteroids, we can better understand what makes our solar system typical or unique. Perhaps certain chemical signatures we see in our own small bodies actually originated from ancient interstellar visitors that impacted Earth or other planets. The chemical history of our solar system might be more cosmopolitan than we realized, influenced by messages from many different stars. As we decode these chemical messages, we're participating in a form of cosmic communication that transcends the vast distances and timescales that separate star systems. While we may never achieve direct communication with civilizations around other stars, we can read the messages written in the chemistry of interstellar objects. These messages tell us about the diversity of planetary systems, the processes that shape them, and the potential for life throughout the galaxy. Each interstellar visitor is like a book from a vast cosmic library, and we're just learning how to read. The philosophical implications of these chemical messages are profound. They remind us that all star systems are connected through the exchange of material, that the atoms in our bodies might have originated in many different stars, carried here by processes similar to those that brought 31/ATLAS to our solar system. We're not just observers of the cosmos, but participants in its ongoing chemical evolution. The calcium in our bones, the iron in our blood, the carbon in our DNA, all of these might have travelled as passengers in interstellar objects billions of years ago. Tonight, as you drift towards sleep, consider that above you, beyond the protective atmosphere of Earth, chemical messages from distant stars continue to arrive. Some are carried by objects too small or distant for us to detect, others by visitors like 3I/ATLAS, that briefly grace our skies before returning to the darkness. Each one carries information about its home, about the star that warmed it and the processes that shaped it. In this way, the universe shares its stories with us, written not in words but in the universal language of chemistry. The study of these chemical messages is still in its infancy. We've only detected a handful of interstellar objects, and our ability to analyze their compositions is limited by current technology. But as our capabilities improve, as we detect more visitors and analyze them in greater detail, we'll be able to read these messages more clearly. We'll learn about the diversity of planetary systems, the processes that shape them, and perhaps even find clues about the prevalence of life in the galaxy. Each new detection, each new analysis, adds another page to the cosmic story we're gradually learning to read. As this first part of our journey through the mysteries of 3I/ATLAS and its potential fleet draws toward a close, we find ourselves at the edge of even deeper mysteries. The patterns we've explored, the fleets we've imagined, the messages we've begun to decode, all point toward a galaxy far more dynamic and interconnected than we once believed. But there's still so much more to discover, so many questions yet to be answered about these cosmic wanderers and what they mean for our understanding of our place in the universe. The timing of these interstellar visits raises profound questions that ripple through our understanding of cosmic mechanics and our place within the galaxy's grand choreography. As we continue our journey through these cosmic mysteries tonight, perhaps feeling the gentle pull of sleep beginning to tug at the edges of your consciousness like a soft tide lapping at the shore, let's explore why we're detecting these visitors now, after centuries of watching the skies, and what this timing might reveal about cycles and patterns that operate on scales far beyond human experience. The appearance of objects like 3I/ATLAS at this particular moment in human history isn't just coincidence. It's the intersection of technological capability, cosmic positioning, and perhaps something even more fundamental about the rhythm of interstellar exchanges. Consider for a moment the extraordinary fact that humans have been systematically observing the night sky for thousands of years, from the ancient astronomers of Babylon and Egypt to the medieval scholars of the Islamic world, from Galileo's first telescopic observations to the massive surveys of the 20th century. Yet, in all that time, we never detected a confirmed interstellar visitor until 2017. Then suddenly, within just a few years, we found multiple objects that definitely came from beyond our solar system. This clustering of discoveries begs the question, what changed? Is it simply that our technology finally crossed a threshold of sensitivity, or is there something special about this particular era in cosmic terms? The technological explanation is certainly part of the story. Modern astronomical surveys use digital cameras with sensitivities that would have seemed magical to astronomers just a generation ago. These instruments can detect objects millions of times fainter than what the human eye can see, and they can cover vast areas of sky in a single night. Computer algorithms automatically compare images taken minutes apart, flagging anything that moves against the background stars. This automation means we can monitor the sky continuously, never missing a potential discovery because someone needed to sleep or take a break. The Panoramic Survey Telescope and Rapid Response System, or PAN-STARRS, which discovered Oumuamua, represents exactly this kind of capability, scanning the entire visible sky multiple times per month. But technology alone doesn't fully explain the timing. After all, We've had reasonably sensitive electronic detectors for decades, and computers capable of automated detection for at least 20 years. The sudden cluster of discoveries suggests that something else might be at play, something about the current epoch that makes interstellar visitors either more common or easier to detect. This brings us to one of the most intriguing aspects of the timing question: the possibility that the frequency of interstellar visits actually varies over time, following patterns and cycles we're only beginning to understand. Our solar system isn't stationary in space, but follows a complex path through the galaxy. We orbit the center of the Milky Way at a speed of about 220 kilometers per second, completing one galactic year every 225 million Earth years. But this isn't a simple circular orbit. The solar system also oscillates up and down through the galactic plane, like a horse on a carousel that moves up and down as it goes around. This vertical oscillation has a period of about 70 million years, meaning we pass through the densest part of the galactic disk roughly every 35 million years. During these passages, we encounter more stars, more molecular clouds, and potentially more interstellar objects. The timing of our current position in this galactic oscillation is particularly interesting. According to recent calculations, we're currently very close to the midplane of the galaxy, having crossed it just a few million years ago in cosmic terms. This positioning might mean we're in a region of enhanced interstellar object density, a cosmic highway where these wanderers are more common. If this hypothesis is correct, the detection of 3I/ATLAS and its companions might herald a period of increased activity that could last millions of years. The variations would be subtle and play out over many generations. There's also the fascinating possibility that our solar system is currently passing through a stream or cloud of interstellar objects, a concentrated region where these visitors are more common. Such streams could be created by the disruption of a planetary system millions of years ago, with the debris spreading out along the orbital path of the disrupted system's parent star. If we're passing through such a stream now, it would explain why we're suddenly detecting multiple interstellar objects after centuries of seeing none. The stream might be vast, taking centuries or millennia to pass through completely, meaning we could be in for an extended period of frequent interstellar visitors. The role of the solar system's motion relative to the local standard of rest adds another layer to the timing puzzle. The local standard of rest is the average motion of stars in our neighborhood, and our Sun has its own peculiar velocity relative to this average. This peculiar velocity changes over time due to gravitational interactions with passing stars and molecular clouds. Currently, we're moving at about 20 kilometers per second relative to the local standard of rest, but this velocity and direction change over millions of years. These changes affect which populations of interstellar objects we encounter and at what rates. Seasonal variations in our ability to detect interstellar objects create short-term timing patterns overlaid on these longer cosmic cycles. Earth's orbit around the Sun means that different parts of the sky are visible at different times of year, and the Sun's glare blocks out large regions where interstellar objects might be lurking. Objects approaching from certain directions are much easier to detect at specific times of year, creating windows of opportunity that repeat annually. The timing of 3I/ATLAS's discovery was influenced by these seasonal factors, and understanding them is crucial for planning future searches. The evolution of our technological capabilities creates its own timing effects that must be carefully separated from genuine variations in the interstellar object population. Each improvement in telescope sensitivity, each new survey that comes online, increases our detection rate in a step-like fashion. The launch of new space telescopes, free from the interference of Earth's atmosphere, will create additional jumps in our detection capability. We're living through a revolution in astronomical observation, and the timing of discoveries is partly a reflection of this technological transformation. But perhaps the most profound aspect of the timing question relates to the age of our solar system and its current evolutionary state. At 4.6 billion years old, our solar system has reached a kind of middle age, where the orbits of planets are stable and predictable. The chaotic early period when planets migrated and countless objects rejected is long past. This stability might make us more sensitive to perturbations from passing interstellar objects, allowing us to detect their gravitational influences on our own small bodies, even when we can't see the interstellar objects directly. The timing of interstellar object arrivals might also be influenced by recent stellar encounters that we're not yet aware of. Stars passing within a few light years of our solar system can perturb the Oort cloud, sending comets into the inner solar system and potentially affecting the trajectories of passing interstellar objects. The star Gliese 710 is currently approaching our solar system and will pass within 1.1 light-years in about 1.3 million years. But there might have been other encounters in the recent past that we haven't identified. These encounters could focus interstellar objects toward the inner solar system, creating temporary increases in the detection rate. The relationship between the timing of interstellar object detection and solar activity presents another intriguing avenue of investigation. The Sun's magnetic field and solar wind create a bubble around our solar system called the heliosphere, and this bubble varies in size and shape with the 11-year solar cycle. During solar maximum, when the Sun is most active, the heliosphere expands, potentially affecting the trajectories of small interstellar objects. We've only been detecting interstellar objects for one solar cycle, so we don't yet know if there's a correlation, but it's a possibility that astronomers are watching carefully. Long-term climate cycles on Earth might also influence our ability to detect interstellar objects, though this connection is more subtle. During ice ages, when more of Earth's water is locked up in glaciers, the atmosphere is typically drier and clearer, potentially improving astronomical observations. Conversely, during warm periods, increased atmospheric water vapor could make observations more difficult. We're currently in an interglacial period, but the anthropogenic climate change we're experiencing is creating unprecedented conditions, whose effects on astronomical observations are still being assessed. The timing question also extends to individual objects and their specific orbital characteristics. 3 I/ATLAS approached our solar system from a direction that made it relatively easy to detect with current surveys, but objects approaching from other directions might go unnoticed. The timing of an object's closest approach to the Sun, its perihelion, determines when it's brightest and easiest to study. Objects that reach perihelion when they're on the opposite side of the Sun from Earth are much harder to observe than those that reach perihelion when they're well placed in our night sky. The possibility that interstellar object arrivals are correlated with mass extinction events on Earth adds a sobering dimension to the timing question. Some scientists have proposed that impacts from interstellar objects, being typically faster than local comets and asteroids, could be particularly devastating. The timing of past mass extinctions shows some periodicity, roughly every 26 to 30 million years, which some researchers have tried to link to our solar system's motion through the galaxy. While this connection remains controversial, the detection of actual interstellar objects gives us new data to test these hypotheses. Cultural and sociological factors also influence the timing of discoveries in unexpected ways. The detection of Oumuamua generated enormous public interest and scientific excitement, leading to increased funding for surveys and more telescope time dedicated to searching for interstellar objects. This positive feedback loop means that each discovery makes the next one more likely, at least in terms of our ability to detect it. The timing of 3I/ATLAS's discovery, coming when the scientific community was already primed to look for such objects, might not be entirely coincidental. The development of artificial intelligence and machine learning has created a revolution in our ability to process astronomical data, and the timing of this revolution coincides with our detection of interstellar objects. These algorithms can identify subtle patterns in data that human observers might miss, and they can process vast amounts of information in real time. As these systems become more sophisticated, they might reveal that we've actually been observing interstellar objects for years without recognizing them, hidden in archived data waiting to be discovered. Looking toward the future, the timing of upcoming discoveries will be influenced by several major astronomical facilities currently under construction. The Vera Rubin Observatory, formerly known as the Large Synoptic Survey Telescope, will begin operations soon and will survey the entire visible sky every few nights. The European Space Agency's Euclid mission and NASA's Nancy Grace Roman Space Telescope will provide unprecedented sensitivity for detecting faint objects. The timing of 3I/ATLAS's discovery might be remembered as the beginning of a golden age of interstellar object detection. The question of whether we're living in a special time for interstellar object detection touches on deeper philosophical issues about our place in cosmic history. Are we fortunate to be alive at just the moment when technology and cosmic circumstances align to reveal these visitors? Or is every era special in its own way, with its own discoveries waiting to be made? The timing of our existence, at a moment when we can detect and study objects from other star systems but cannot yet travel to those systems ourselves, creates a unique perspective on our cosmic situation. The synchronized timing of multiple technological and scientific developments creates what some researchers call a discovery window for interstellar objects. This window opened with the combination of sensitive digital detectors, automated surveys, fast computers for data processing, and a theoretical framework for understanding what we're seeing. The window might close if future technology makes direct interstellar travel possible, shifting our focus from detecting visitors to becoming visitors ourselves. We're living in the brief historical moment when interstellar objects are exotic discoveries, rather than routine observations or accessible destinations. As we contemplate these questions of timing tonight, we're really exploring the intersection of human consciousness with cosmic cycles that operate on scales almost beyond imagination. The detection of 3I/ATLAS at this particular moment represents the convergence of so many factors: the evolution of our technology, the position of our solar system in the galaxy, the possible passage through streams of objects, the state of our scientific understanding. Each of these factors has its own timeline, its own rhythm, and they've all synchronized at this moment to reveal these cosmic visitors to our wondering eyes. In the cold spaces between stars, more than rock and ice might be travelling through the eternal darkness, carrying cargoes that could fundamentally alter our understanding of how the galaxy shares its treasures across the vast distances that separate stellar islands. As your consciousness continues to soften around the edges tonight, drifting like a boat on calm waters toward the shores of sleep, let's explore what else might accompany objects like 3I/ATLAS on their interstellar journeys. Complex molecules, perhaps even the building blocks of life itself, could be drifting through eternity, passengers on these cosmic vessels that sail the dark seas between stars. The concept of interstellar objects as carriers goes far beyond simple chunks of rock or ice moving through space. These objects are potentially transport mechanisms for a vast array of materials, from the simplest atoms to complex organic molecules, from microscopic dust grains to perhaps even dormant microorganisms. Each interstellar visitor is like a cosmic shipping container, its cargo manifest written in the language of chemistry and physics, carrying goods that were loaded millions or billions of years ago in distant star systems. The implications of this cosmic commerce are staggering, suggesting that the galaxy might be far more interconnected than we ever imagined, with star systems exchanging materials in a vast, slow, but continuous trade network. Let's begin with the simplest cargo, atoms and molecules. When an object like 3I/ATLAS forms in a protoplanetary disk, it incorporates whatever materials are available in its local environment. This includes not just the common elements like hydrogen, carbon, nitrogen and oxygen, but also trace elements that might be rare in one star system but common in another. These atomic passengers remain locked in the object's structure for the duration of its interstellar journey, preserved in the deep freeze of space. When such an object enters another star system, it brings with it this collection of atoms, potentially introducing elements or isotopes that are rare in the destination system. The preservation of these atomic cargoes in the extreme cold of interstellar space is remarkably effective. At temperatures just a few degrees above absolute zero, chemical reactions essentially cease, and even the slow process of radioactive decay becomes the primary agent of change. This means that radioactive isotopes in interstellar objects act like clocks, recording the time since the object was last heated or processed. By measuring the ratios of parent and daughter isotopes, scientists can determine not just what an object is made of, but when it formed and how long it's been travelling. But atoms are just the beginning. Molecules, combinations of atoms bound together by chemical forces, represent a far more interesting and complex cargo. In the cold depths of interstellar objects, molecules that would be unstable under warmer conditions can survive for enormous periods. Water ice, of course, is the most common molecular solid in the universe, but interstellar objects can also contain methane, ammonia, carbon dioxide, and a vast array of more complex molecules. Each of these molecular species tells a story about the conditions under which the object formed and the chemical processes that were active in its parent system. The discovery of increasingly complex organic molecules in space has revolutionized our understanding of cosmic chemistry. Molecules containing dozens of atoms, including amino acids and other prebiotic compounds, have been detected in interstellar clouds, comets, and meteorites. If interstellar objects carry similar molecular cargoes, they could be distributing the building blocks of life throughout the galaxy. Imagine 3I/ATLAS carrying within its icy matrix a collection of amino acids formed around another star. Molecules that could, under the right conditions, participate in the chemistry of life. The concept of panspermia, the idea that life might spread between star systems, takes on new dimensions when we consider interstellar objects as potential carriers. While the harsh radiation environment of interstellar space would likely destroy any active life on the surface of these objects, the interiors might provide sufficient shielding for dormant microorganisms to survive. Bacterial spores, known for their incredible resilience, might be able to withstand the journey, especially if embedded deep within a large object. The periodic passage of interstellar objects through our solar system means that Earth has likely been exposed to material from thousands of different star systems over its history. The role of cosmic rays in processing the cargo of interstellar objects adds another layer of complexity. These high-energy particles streaming through space from supernovae and other energetic events can break apart molecules and create new ones through a process called radiolysis. Over millions of years, this processing can create a rich chemistry on the surfaces of interstellar objects, producing complex organic molecules from simpler precursors. The surface of an object like 3I/ATLA might be covered in a dark, organic-rich crust created by eons of cosmic ray bombardment, a kind of natural chemical factory powered by the galaxy's most energetic events. Dust grains represent another fascinating category of interstellar cargo. These microscopic particles, often smaller than the width of a human hair, can contain an enormous amount of information about their origins. Some dust grains, called pre-solar grains, formed around other stars and have been found in meteorites that fall to Earth. These grains survived the formation of our solar system and carry isotopic signatures that identify them as foreign. Interstellar objects likely carry countless such grains, each one a messenger from a different star, creating a kind of cosmic library written in dust. The magnetic fields frozen into interstellar objects provide yet another type of cargo, one that's invisible but potentially significant. When these objects form in the magnetic environment of a protoplanetary disk, they can trap and preserve those magnetic fields in their structure. As they travel through interstellar space and encounter the varying magnetic fields of the galaxy, these preserved fields interact with their environment in complex ways. The magnetic cargo of interstellar objects might influence how they interact with the solar wind and planetary magnetospheres when they pass through star systems. The possibility that interstellar objects might carry technological artifacts, while highly speculative, cannot be entirely dismissed. If intelligent civilizations exist elsewhere in the galaxy, and if they engage in space activities that produce debris, some of that debris might eventually escape into interstellar space. Over the billions of years of galactic history, the accumulated technological debris from thousands or millions of civilizations could create a small but fascinating component of the interstellar object population. While the probability of detecting such an artifact is vanishingly small, the implications would be transformative. Water, that most essential molecule for life as we know it, deserves special consideration as interstellar cargo. The detection of water ice in comets from our own solar system has shown that these objects can be enormous reservoirs of water. If interstellar objects carry similar amounts of water, they could be important contributors to the water inventory of planetary systems. The early Earth might have received significant amounts of water from interstellar impacts, water that originated around other stars and travelled for millions of years to reach our planet. Every glass of water you drink might contain molecules that have journeyed between the stars. The isotopic composition of materials carried by interstellar objects provides crucial information about nucleosynthesis, the process by which elements are created in stars. Different types of stars and different stellar processes produce different isotopic ratios. For example, the ratio of carbon-12 to carbon-13 or oxygen-16 to oxygen-18 varies depending on the stellar environment. By measuring these ratios in interstellar objects, we can learn about the types of stars that contributed material to their formation, creating a kind of stellar genealogy traced through isotopes. Complex organic molecules deserve particular attention as interstellar cargo because of their relevance to the origin of life. Laboratory experiments have shown that the types of organic molecules found in meteorites can, under the right conditions, form more complex structures, including vesicles that resemble primitive cell membranes. If interstellar objects carry similar organic inventories, they could seed planetary systems with the molecular toolkit needed for life to emerge. The impact of an organic-rich interstellar object on a young planet with liquid water could create a kind of natural laboratory for prebiotic chemistry. The role of interstellar objects in transporting volatile compounds between star systems has implications for planetary atmospheres. Volatiles like nitrogen, carbon dioxide, and noble gases are essential components of planetary atmospheres, but can be lost to space through various processes. The impact of volatile-rich interstellar objects could replenish these atmospheric components, potentially maintaining habitable conditions for longer periods. Earth's atmosphere might owe some of its stability to occasional deliveries of volatiles from interstellar space. Mineral grains within interstellar objects carry information about the geology of other worlds. These grains formed under specific conditions of temperature, pressure, and chemical environment that might be very different from those in our solar system. Some minerals might be completely unknown to us, stable only under conditions that don't exist in our planetary system. The study of mineral cargo in interstellar objects could reveal new types of planetary geology, expanding our understanding of the possible varieties of rocky worlds. The concept of molecular clouds as waypoints for interstellar objects adds another dimension to what travels between stars. As these objects pass through the dense regions of molecular clouds, they can accumulate additional material, adding new cargo to their manifest. This process means that an interstellar object might carry materials not just from its parent system, but from multiple environments it encountered during its journey. Each object becomes a kind of cosmic sampler, collecting materials from different regions of the galaxy. The preservation of biological signatures in interstellar objects, if they exist, would depend on the specific conditions within the object. While surface materials would be heavily processed by radiation, the interiors of large objects might preserve biosignatures for enormous periods. These signatures might not be living organisms, but rather the chemical fossils of life, specific patterns of organic molecules, isotopic fractionations characteristic of biological processes, or mineral structures that form only in the presence of life. The discovery of such signatures in an interstellar object would revolutionize our understanding of life in the universe. The cargo capacity of interstellar objects varies enormously with their size and composition. A small, rocky object might carry little more than its constituent minerals, and a thin coating of radiation-processed organics. But a large, icy object like 3I/AT LAS could carry vast amounts of water, complex organics, and potentially preserved materials from its parent system's early history. The largest interstellar objects, those the size of dwarf planets or larger, could carry entire chemical laboratories within their interiors, places where complex chemistry might continue even during the long journey between stars. The exchange of materials between star systems via interstellar objects creates a kind of galactic metabolism, a slow but continuous cycling of materials that connects all star systems in subtle ways. Just as Earth's biosphere cycles carbon, nitrogen, and other elements through various reservoirs, the galaxy cycles materials through star systems, interstellar space, and molecular clouds. Interstellar objects are crucial components of this cycling, carrying materials from regions of production to regions of consumption, maintaining a dynamic equilibrium that has operated for billions of years. The implications of this cosmic cargo exchange for the search for life are profound. If life's building blocks are routinely transported between star systems, then the emergence of life might not require special conditions unique to a particular planet. Instead, life might emerge wherever and whenever conditions allow the assembly of these cosmic ingredients into self-replicating systems. The galaxy might be seeded with the potential for life, waiting only for the right conditions to trigger its emergence. As we consider what travels between the stars, we're forced to expand our perspective from isolated star systems to an interconnected galaxy where materials and perhaps information flow continuously between stellar islands. The detection of 3I/ATLAS and other interstellar objects gives us our first direct glimpse of this cosmic commerce, these cargo ships that have been sailing the dark seas of interstellar space since the galaxy was young. Each object that passes through our solar system brings gifts from distant stars, materials forged in alien suns and processed in unknown planetary systems. Throughout Earth's history, countless interstellar objects have passed by unnoticed, silent witnesses to the grand story of our planet's evolution, watching as continents formed and split apart, as life emerged from primordial seas and colonized the land, as dinosaurs rose to dominance and fell to extinction, all while maintaining their eternal vigil from the darkness beyond. As you sink deeper into relaxation tonight, perhaps feeling your awareness becoming as vast and quiet as the spaces between stars, let's contemplate these silent watchers that have been constant companions to our solar system's journey through cosmic time, present for every major event in Earth's history, yet remaining forever beyond our ancestors' ability to perceive them. The concept of silent watchers transforms our understanding of Earth's cosmic environment from one of isolation to one of constant, if distant, companionship. Based on current estimates of interstellar object density, there might be thousands of these objects within the orbit of Neptune at any given moment, and millions more in the vast sphere of the Oort cloud that surrounds our solar system. They drift through our cosmic neighborhood like ghost ships in the night, most too small or too distant to detect with current technology, but present nonetheless, maintaining their silent watch over the unfolding drama of planetary evolution. Consider the extraordinary span of time over which these watchers have been present. Earth formed 4.6 billion years ago from the collapsing disk of dust and gas that surrounded our young sun. even as our planet was still accreting, still glowing with the heat of countless impacts, interstellar objects were passing through the solar system. Some of these early visitors might have contributed to Earth's growth, impacting the young planet and adding their materials to the growing world. These ancient watchers witnessed the formation of the Moon, that cataclysmic event when a Mars-sized object struck Earth and threw vast amounts of material into orbit. During the late heavy bombardment, that period about 4 billion years ago when the inner solar system was pelted with asteroids and comets, interstellar objects continued their passages. While the solar system's own small bodies were raining down on the young Earth, creating the heavily cratered surfaces we still see on the Moon and Mercury, the silent watchers from other star systems drifted by, unaffected by the local chaos. They carried with them the memory of other planetary systems' formation, other late heavy bombardments around distant stars, creating a kind of cosmic continuity that links the violent early history of all planetary systems. The emergence of life on Earth, that momentous transition from chemistry to biology that occurred at least 3.5 billion years ago, took place under the distant gaze of these interstellar watchers. As the first self-replicating molecules formed in warm pools or deep-sea vents, as the first cells developed and began the long journey of evolution, objects from other star systems continued their passages through our solar system. Some scientists speculate that these watchers might have been more than passive observers, that impacts from interstellar objects might have delivered crucial organic molecules or even primitive life itself to the young Earth. Through the long ages of the Proterozoic, when life remained microscopic and Earth's atmosphere slowly filled with oxygen produced by photosynthetic bacteria, the silent watchers maintained their vigil. They were present when the first eukaryotic cells evolved, when the first multicellular organisms appeared, when the strange Ediacaran fauna emerged and disappeared. Each of these evolutionary milestones occurred while interstellar objects traced their paths through the solar system, carrying their ancient cargoes past a world that was slowly transforming from a bacterial planet to one capable of supporting complex life. The Cambrian explosion, that remarkable period about 540 million years ago, when most major animal phyla appeared in the fossil record, unfolded while interstellar watchers passed overhead. As trilobites scuttled across ancient seafloors and the first vertebrates evolved, objects from distant stars continued their eternal journeys through our cosmic neighborhood. These watchers had seen similar explosions of diversity around other stars, or perhaps they came from systems where life never emerged at all, making them witnesses to something truly special and rare. During the age of dinosaurs, spanning more than 180 million years, countless interstellar objects passed through the solar system. They were present when the first dinosaurs evolved from smaller reptilian ancestors, when the giant sauropods reached their maximum size, when flowering plants first appeared and transformed terrestrial ecosystems. The silent watchers were overhead when Tyrannosaurus rex stalked its prey, and when Triceratops browsed on cycads and ferns. They maintained their vigil through the entire Mesozoic era, accumulating in their trajectories the gravitational memory of Earth as it was during the Age of Reptiles. The asteroid impact that ended the dinosaurs' reign 66 million years ago occurred while interstellar watchers looked on. As the Chicxulub impactor struck the Yucatan Peninsula, sending shock waves around the globe and throwing vast amounts of debris into the atmosphere, objects from other star systems continued their passages unperturbed, they witnessed the immediate devastation and the long nuclear winter that followed, the mass extinction that cleared the way for mammals to inherit the Earth. Some of these watchers might have passed close enough to Earth to have their trajectories slightly altered by our planet's gravity, carrying with them into interstellar space a subtle record of Earth's mass at that crucial moment in biological history. The rise of mammals and the eventual evolution of primates took place under the continuing surveillance of these cosmic observers. As the first apes evolved in Africa, as early hominids began walking upright, as our ancestors developed tools and language and culture, interstellar objects maintained their passages through the solar system. They were present when Homo sapiens first appeared, when we developed agriculture and built the first cities, when we began to wonder about our place in the universe. Every moment of human history has been witnessed by these silent watchers, even though we've only recently become aware of their presence. The technological revolution that has transformed human society over the past few centuries has been observed by passing interstellar objects. They were overhead when we invented the telescope and first turned it toward the heavens, when we discovered that other planets orbit other stars, when we realized the true scale of the universe. The irony is profound. As we developed the tools to detect these watchers, they had been there all along, maintaining their silent vigil over our progress. The recent detection of objects like 3I/ATLAS represents not the arrival of something new, but our first awareness of something that has always been present. The gravitational influence of these silent watchers on our solar system, while individually tiny, might be collectively significant over geological timescales. Each passing object exerts a minute gravitational pull on the planets, asteroids, and comets of our solar system. Over billions of years, these countless small perturbations could have altered orbits, triggered impacts, or stabilized configurations that might otherwise have been unstable. The solar system we see today, with its remarkably stable planetary orbits, might owe some of that stability to the cumulative effect of interstellar encounters. The information carried by these watchers about Earth's history is fascinating to contemplate. Any interstellar object that passed close to Earth would have its trajectory altered by our planet's gravity, and the magnitude of that alteration would depend on Earth's mass at the time. Since Earth's mass has grown over geological time through the accretion of impacting objects, each watcher carries information about Earth's mass at the time of its passage. If we could somehow track all the interstellar objects that have passed through our solar system and measure their trajectories precisely, we could in principle reconstruct the growth history of Earth and the other planets. The possibility that some of these silent watchers might have been captured into orbit around the Sun adds another dimension to their story. Gravitational interactions with planets, particularly Jupiter, could occasionally slow an interstellar object enough for it to become bound to our solar system. Some astronomers have suggested that certain unusual objects in our solar system, particularly those with highly inclined or retrograde orbits, might be captured interstellar objects. If true, these naturalized citizens of our solar system would be the only watchers we can study in detail, ancient visitors that decided to stay. The role of silent watchers in delivering volatiles to Earth throughout its history could have been crucial for maintaining our planet's habitability. Earth has lost atmosphere to space over billions of years, particularly lighter elements like hydrogen and helium. Impacts from volatile-rich interstellar objects could have partially compensated for these losses, helping to maintain the atmospheric pressure and composition necessary for liquid water and life. Every breath we take might contain atoms delivered by these cosmic watchers over Earth's long history. These silent watchers have also been present for Earth's climate variations, from the snowball Earth episodes when our planet was frozen from pole to pole, to the hothouse periods when palm trees grew in Antarctica. They've witnessed ice ages come and go, seen the continents drift from one configuration to another, observed as mountain ranges rose and eroded away. Each of these changes affected Earth's gravitational field slightly, information that would be encoded in the trajectories of passing objects. The watchers carry with them a gravitational record of Earth's changing shape and mass distribution. The philosophical implications of these silent watchers are profound. They remind us that Earth's story has always had an audience, even if that audience consists of unconscious chunks of rock and ice. Every triumph and tragedy in Earth's history, every evolutionary innovation and extinction event has been observed by these passing objects. They've been the ultimate impartial observers, recording in their trajectories and compositions the story of our solar system without judgment or interference. The search for evidence of past interstellar encounters in Earth's geological record is an active area of research. Some scientists have looked for unusual isotopic ratios in ancient sediments that might indicate material from interstellar impacts. Others have searched for correlations between proposed interstellar encounters and extinction events or climate changes. While no smoking gun has been found, the possibility remains that some of Earth's geological mysteries might be explained by interactions with these silent watchers. The cultural impact of recognizing these silent watchers extends beyond science into philosophy, art, and spirituality. The knowledge that Earth has never been truly alone, that witnesses from other star systems have always been present, changes our narrative about our planet's place in the cosmos. We're not isolated actors on a cosmic stage, but part of an interconnected galaxy, where every star system is observed by emissaries from every other system. This cosmic surveillance network has operated since the galaxy was young and will continue long after Earth itself is gone. The future observations of silent watchers promise to reveal even more about their nature and significance. Next-generation telescopes will be able to detect smaller and more distant interstellar objects, potentially revealing the full population of watchers in our solar system at any given time. We might discover that certain regions of our solar system are preferred paths for these objects, cosmic highways where the watchers are concentrated. We might find evidence of ancient encounters in the orbits of solar system bodies, or in the cratering records of airless worlds. The possibility of sending spacecraft to intercept and study these silent watchers represents the next phase in our relationship with them. Instead of passive observation, we could actively engage with these cosmic visitors, landing on them, sampling their materials, perhaps even using them as platforms for interstellar travel. The watchers that have observed Earth's history could become stepping stones for humanity's expansion into the galaxy, transforming from silent observers to active participants in our cosmic future. As we contemplate these silent watchers tonight, drifting through space on their eternal journeys, we're reminded of the deep time over which cosmic processes operate. Human civilization has existed for only the briefest moment compared to the age of these watchers, some of which have been travelling since before our solar system formed. Yet in that brief moment we've developed the ability to detect and study them, to recognise their presence and appreciate their significance. We've become aware of the watchers, transforming them from completely silent observers to partners in our quest to understand the cosmos. The story of the silent watchers is still being written. Each new detection adds another chapter, another perspective on Earth's cosmic environment. Objects like 3I/ATLAS are just the most recent and visible of these watchers, representatives of a vast population that has been present throughout Earth's history. As our detection capabilities improve, we'll undoubtedly discover more of these cosmic observers, each one carrying information about distant star systems and bearing witness to our ongoing journey through space. The recognition that we've always been watched in a sense by these cosmic wanderers adds a new dimension to our understanding of Earth's story. Every major event in our planet's history, from the formation of the oceans to the emergence of consciousness, has taken place in the presence of these visitors from other stars. They've been the silent witnesses to the grand experiment of life on Earth, carrying in their trajectories and compositions a record of our planet's evolution that extends far beyond Earth itself. As you drift towards sleep tonight, perhaps feeling your consciousness becoming as soft and expansive as the cosmic darkness itself, consider the infinite journeys happening above you at this very moment, the eternal voyages of objects like 3I/ATLAS, that connect distant shores across the vast ocean of space, carrying dreams of worlds we'll never see and messages from stars whose light has travelled for centuries to reach our eyes. This final chapter of our cosmic contemplation brings us full circle from the specific discovery of 3I/ATLAS to the grand vision of a galaxy where every star system is connected by threads of wandering matter, where the dreams of one world become the seeds of another, where the boundaries between stellar systems blur into a continuous exchange of materials, information, and perhaps even life itself. The concept of distant shores takes on profound meaning when we consider interstellar objects as bridges between worlds. Each star system is like an island in the vast darkness, separated from its neighbours by distances so enormous that light itself takes years to cross them. Yet these islands are not truly isolated. They're connected by streams of wandering objects, each one a messenger, a bottle cast into the cosmic ocean, carrying information about its place of origin. 3I/Atlas might indeed be part of a vast fleet, but even if it travels alone, it represents this fundamental connection between stellar shores, a physical link between our solar system and another place in the galaxy where different suns shine on different worlds. Tonight, as your breathing deepens and your thoughts begin to drift like clouds across the landscape of consciousness, imagine the journey that 3I/ATLAS has taken to reach us. Picture its formation billions of years ago in a disk of dust and gas surrounding a young star. Perhaps a star similar to our Sun, or perhaps something quite different. A red dwarf that would shine steadily for trillions of years, or a blue giant that would burn bright and die young. In that alien stellar nursery, atoms came together to form molecules. Molecules aggregated into grains. Grains accumulated into pebbles. And pebbles grew into the mountain-sized object that would eventually visit our solar system. Consider the violence of its ejection from that primordial home, perhaps flung outward by the gravity of a forming gas giant, accelerated to speeds that would carry it beyond the gravitational embrace of its parent star. That moment of ejection was both an ending and a beginning, the end of its connection to its birthplace, and the beginning of an odyssey that would last longer than the current age of the universe. As it crossed the boundary into interstellar space, 3I/ATLAS became a cosmic orphan, but also a messenger, carrying within its frozen heart the chemical signature of its home. The dreams of distant shores are encoded in the very atoms that make up these interstellar wanderers. Every element heavier than hydrogen was forged in the nuclear furnace of a star, or in the violent explosion of a supernova. The carbon atoms in 3I/ATLAS might have been created in a star that died billions of years before our sun was born. The oxygen might have come from a different star entirely. These atoms have their own stories, their own journeys through the galaxy, and 3I/ATLAS has brought them together in a configuration that tells us something about conditions in another part of the galaxy, at another time in cosmic history. As you continue to relax, letting the tensions of the day dissolve into the softness of your pillow, think about what other shores 3I/ATLAS might have passed during its journey. Over millions of years, it might have drifted through stellar nurseries where new stars were being born, their light just beginning to pierce the surrounding clouds of gas and dust. It might have passed through the outskirts of other planetary systems, too distant to be captured but close enough to glimpse worlds we can only imagine. Each close encounter would have slightly altered its trajectory, adding another chapter to its story, another memory to its long journey between the stars. The possibility that 3I/ATLAS is part of a fleet transforms our vision from a single messenger to an armada of dreams, each object carrying its own piece of the story. If thousands or millions of objects were ejected from the same stellar system, they would spread out over time like seeds from a cosmic dandelion, each one following its own path but all sharing a common origin. Some might have already passed through our solar system centuries or millennia ago, unnoticed by our ancestors who lacked the technology to detect them. Others might be approaching even now, years or decades away from their closest approach to our sun. The dreams carried by these cosmic wanderers aren't just about the past, they're also about the future. Every interstellar object that passes through our solar system has the potential to influence our future in subtle ways. A close encounter with Earth could deliver new materials to our planet. A collision with an asteroid could alter its orbit, potentially affecting future impact risks. Even the gravitational perturbations from passing objects, tiny as they are, accumulate over time to shape the evolution of our solar system. We are not just observers of these cosmic dreams, but participants in them, our world shaped by the accumulated influence of countless interstellar encounters. In the gentle darkness of your room tonight, as sleep begins to embrace you like the vast darkness embraces these cosmic wanderers, consider that somewhere in the galaxy, objects ejected from our own solar system are carrying Earth's dreams to distant shores. Billions of years ago, during the chaotic early days of planetary formation, our solar system sent its own messengers into interstellar space. These objects, bearing the chemical signature of our sun and the materials that didn't quite make it into planets, are now visiting other star systems, telling them the story of our cosmic neighborhood. The interconnectedness revealed by objects like 3I/ATLAS suggests that the galaxy might be far more hospitable to the spread of life than we once imagined. If organic molecules, or even primitive life forms, can survive the journey between stars protected within these cosmic arcs, then life might not need to arise independently on every inhabited world. Instead, it might spread like seeds on a cosmic wind, taking root wherever conditions are suitable. The dreams of life on one world could become the reality of life on another, creating a vast network of biological connections across the galaxy. The technological implications of these interstellar fleets stretch our imagination toward futures where humanity might harness these cosmic currents. Perhaps one day we'll be able to predict the arrival of interstellar objects with enough precision to send spacecraft to intercept them. We could hitch rides on these cosmic wanderers, using them as platforms for telescopes or even as generation ships for interstellar colonization. The dreams of reaching distant shores might be realized not through massive rockets, but through patient waiting for the right cosmic bus to come along. As your eyelids grow heavy and your thoughts become increasingly dreamlike, mixing the real with the imagined in that special way that happens at the boundary of sleep, think about the profound shift in perspective that 3I/ATLAS represents. For all of human history, we've looked at the stars as distant lights, unreachable and separate from our world. But these interstellar visitors show us that the stars are not just lights, but places, sources of objects that we can touch and study. The distant shores are not completely unreachable. Pieces of them come to us, carried by patient messengers that have been travelling since before Earth existed. The dreams of distant shores also encompass the possibility of intelligence elsewhere in the galaxy. If technological civilizations exist around other stars, they too must have detected interstellar objects passing through their systems. They might have had their own 3IATLAS moments, their own recognition that they're part of a connected galaxy. Perhaps they've gone further than we have, actually visiting and studying these objects, or even using them to send messages or artifacts to other star systems. The fleet of objects passing through our solar system might include not just natural wanderers, but intentional messengers, though distinguishing between the two might be beyond our current capabilities. The philosophical implications of these cosmic connections invite us to reconsider our place in the universe. We're not isolated beings on an isolated world, but part of a vast web of connections that spans the galaxy. The atoms in our bodies have travelled between stars, perhaps carried by objects like 3I/ATLAS. The water we drink, the air we breathe, the ground we walk on, all of it has been influenced by cosmic processes that connect us to distant shores we'll never see. We are, in a very real sense, citizens of the galaxy, made from cosmic materials and influenced by cosmic processes. In the quietness of approaching sleep, as your breathing naturally deepens and slows, matching the patient rhythms of cosmic time, consider how the discovery of 3I/ATLAS and its potential companion objects might be remembered by future generations. Perhaps it will be seen as the moment when humanity first became aware of the true nature of our cosmic environment, when we realized that the spaces between stars are not empty but filled with wandering worlds. Perhaps it will mark the beginning of a new era of cosmic awareness, when we stopped thinking of ourselves as isolated and started recognizing our connections to the rest of the galaxy. The dreams of distant shores carried by these interstellar wanderers are also dreams of time, of deep time that stretches both backward and forward beyond human comprehension. 3I/ATLAS has been travelling for millions of years, and it will continue travelling for millions more. Long after our sun has died and Earth has been consumed or frozen, this object will continue its journey, carrying with it the gravitational memory of its encounter with our solar system. In this way, something of our world will persist in the cosmos, a subtle influence on the trajectory of a cosmic wanderer that will outlast our planet itself. The possibility that we're currently passing through a fleet of interstellar objects adds urgency to our observations and excitement to our dreams. Each new detection might reveal patterns that confirm the fleet hypothesis. We might discover that these objects share common characteristics that point to a shared origin. We might be able to piece together the story of a distant stellar system from the fragments it sent our way. The dreams of those distant shores might become increasingly clear as we gather more pieces of the puzzle. As sleep approaches, bringing its own dreams and journeys through landscapes of the mind, reflect on how the story of 3I/ATL or S connects to the larger story of cosmic evolution. The galaxy is not static but dynamic, constantly recycling materials through stars, planets, and the spaces between. Interstellar objects are part of this recycling, carrying materials from dying systems to nascent ones, from places where elements are created to places where they're incorporated into new worlds. The dreams of distant shores are really dreams of transformation, of matter and energy flowing through different configurations, occasionally organizing itself into patterns complex enough to contemplate its own journey. The comfort we might find in these cosmic connections is profound. We're not alone in the universe, not when messengers from distant stars regularly pass through our neighborhood. We're not disconnected from the cosmos, but intimately woven into its fabric. Every interstellar object that passes by reminds us that we're part of something larger, something that extends across distances and timescales that dwarf human experience but somehow include us in their grand design. The dreams of distant shores are also dreams of home, reminding us that our small world is part of a vast cosmic community. The scientific revolution sparked by the detection of interstellar objects is just beginning. Future discoveries will undoubtedly surprise us, revealing aspects of these cosmic wanderers we haven't imagined. Perhaps we'll discover that some of them are far stranger than we expected, with compositions or structures that challenge our understanding of planetary formation. Perhaps we'll find evidence that some of them have been modified by intelligence, carrying messages or artifacts between star systems. Perhaps we'll learn to read their chemical and physical properties so well that we can reconstruct detailed histories of their parent systems. As your consciousness continues to soften, becoming as diffuse and peaceful as the spaces between stars, consider one final thought about these dreams of distant shores. Every night, as you drift off to sleep, you're participating in a cosmic rhythm that connects you to the universe. The same physical laws that govern the motion of 3I/ATLS through space govern the neurons firing in your brain. The same atoms that make up interstellar wanderers make up your body. The same vast stretches of time that these objects experience in their journey between stars are compressed into your dreams, where seconds can feel like hours and hours like seconds. The story of 3I/ATLAS and its potential fleet is far from over. As you sleep tonight, these objects continue their eternal journeys. New ones are approaching our solar system, carrying their ancient cargoes toward eventual discovery. Others are leaving, having completed their brief passages through our neighborhood, carrying with them subtle alterations to their trajectories that encode information about our solar system. The cosmic dance continues, patient and eternal, connecting distant shores across the darkness. Perhaps tomorrow will bring news of another discovery, another piece of this cosmic puzzle. Perhaps scientists will announce patterns in the data that support the fleet hypothesis, or perhaps they'll discover something even more surprising. The universe has a way of exceeding our imagination, of revealing wonders we hadn't dreamed of. The detection of 3I/ATLAS might be remembered as the beginning of a new chapter in our understanding of the cosmos, a chapter where the boundaries between star systems blur and the dreams of distant shores become part of our waking reality. In the end, the story of 3I/ATLAS is a story about connections, about the threads that bind the galaxy together across impossible distances and incomprehensible spans of time. It's a story about matter and energy, about chemistry and physics, but it's also a story about wonder and possibility. It reminds us that the universe is not cold and empty, but filled with travelers, each one carrying stories of distant places, dreams of other shores. As you drift into sleep tonight, you become part of this story, a conscious observer of cosmic wanderers, a dreamer of distant shores, a participant in the grand exchange of matter and meaning that has been occurring since the galaxy was young and will continue long after we're gone. The gentle darkness embraces you now, as vast and peaceful as the spaces between stars where 3I/ATLAS and its companions drift on their eternal journeys. In your dreams tonight, perhaps you'll visit those distant shores, those places where other suns warm other worlds, where the same laws of physics create different expressions of cosmic possibility. Perhaps you'll ride alongside these interstellar wanderers, seeing the galaxy from their perspective, understanding the deep connections that unite all star systems in a web of travelling matter and information, and perhaps, in that special wisdom that sometimes comes in dreams, you'll understand something profound about our place in the cosmos, something that daylight consciousness can only glimpse, but that becomes clear in the soft darkness of sleep. The cosmos continues its patient dance above you, interstellar objects pursuing their ancient trajectories, stars burning through their nuclear fuel, planets spinning through their orbits, and you, composed of cosmic materials, influenced by cosmic processes, connected to distant shores through threads of matter and time, drift into sleep, joining the eternal rhythm of the universe, becoming one with the vast and beautiful mystery that surrounds us all. The dreams of distant shores become your dreams, and in dreaming them, you participate in the cosmic story that has been unfolding for billions of years and will continue for billions more. A story in which 3I/ATLAS is just one chapter, one messenger, one dream of distant shores in the infinite ocean of space and time.